Hey there guys, this is Mr. Sheeline. This is going to be pretty much just the check your understandings for the Unit 5.3 notes, conservation of momentum in 2 dimensions. So we've just have 3 check your understandings, but this stuff is going to take a while. So actually, I'm going to break this up into 3 videos, 1 video for each check your understanding, because this is decently long, it's decently complicated in its own right. It takes quite a bit of room, quite a bit of time in order to fully understand what's happening. So make sure you have your notes open, make sure you have them available. We're going to go over, again, we're going to start off with the check your understanding number 1. Okay, so we're going to do the check your understanding number 1 here. Okay, so a car with a mass of 1,500 kilograms is traveling at a velocity of 25 meters per second east, and it collides at an intersection with a 2,500 kilogram truck traveling north at a velocity of 20 meters per second. They stick together in this completely inelastic collision. Find the magnitude and direction of the velocity of the wreckage immediately after the collision. So I'm going to first draw out what we're looking at here. And what we're looking at here is we have a car. So this is going to be my car, and I'm going to say like, I'll put a C here for car. We've got this guy moving across at a rate of 25 meters per second. Okay, moving at 25 meters per second. And then we've got a big old truck here that's moving at a rate of 20 meters per second. Okay, and they're going to collide here at this intersection. So this is just drawing what we're looking at, okay? And just what is bound to happen. So this is the situation we've got here, and we should expect that they're going to move, they'll bond together here, the car here, the truck here, okay, and they're going to move in this direction after collision, okay. So they're going to move in some kind of angle this way at some sort of velocity, okay. That's what we should expect. So let's write down what we know, what we don't know. So we've got the mass of the car equaling 1,500 kilograms. We've got the mass of the truck at 2,500 kilograms. We have the initial velocity of the car at 25.0 meters per second to the east, and the initial velocity of the truck moving at 20 meters per second to the north. Okay, and what we're trying to find here is the final velocity of all this. But first I'm going to put down the final mass, which is just going to be the combined mass of these 2 guys, which is just 4,000 kilograms. Okay, and this is what we're trying to find. We're trying to find the final velocity here. But also not just the magnitude of the velocity, but also the direction, right? So, because there will be an angle relative to the horizontal. Okay, so the first way I'm going to show this is arguably the easiest way. It is just using Pythagorean's theorem here in order to find out what the final momentum is. And then from using the momentum, we can divide by the combined mass in order to find the velocity in which they were moving. So let's draw it out first, though. So making this into a triangle, what we know is, what we should understand here is this is the final movement that we should expect here out of this collision. So here's our hypotenuse. Here is here's the velocity of the car. Here is the velocity of or motion, I should say, the motion of the car, the motion of the truck here. Okay, and we'll just write this accordingly. Okay, and we're trying to find this right here. Now, we can't use Pythagorean's theorem, though, to find our final velocity, just using the velocity of the car, the velocity of the truck. We can't do that. We were able to do that in 2-dimensional motion because we were working with 2 objects, or a single object moving in motion, changing direction. Okay, it's a bit different with momentum. With momentum, we have 2 objects with differing masses, and because they have differing masses, that means that we just can't use a squared plus b squared equals c squared. No, because the mass of the truck is going to adversely affect the mass of the car here. and pretty much the other way around as well, that the car will adversely affect the mass of the truck. And we have to take that into account. They are not separate, or sorry, they are not the same here, and so we can't just use Pythagorean's theorem in order to find the final velocity. But where we can find final velocity using Pythagorean's theorem is just first calculating the final momentum, or sorry, finding the momentum of each of these separate units here. So the momentum of the car is just 25 times the, 1,500? Yeah, 1,500. So then the momentum of the car, let's see, momentum of the car, 37,500 kilograms by meters per second. Whereas the momentum of the truck is going to be, same equation, but it'll be 20 times 2,500, which is going to give us 50,000 kilograms by meters per second. Okay. Now, we now have units, or we now have units and also measurements that take into account both the velocity and the mass. We can use this using a squared plus b squared equals c squared in order to find the final momentum of these two objects. So let's just do that. So that would be, just to solve it straight out, that would be, c is equal to the square root of a squared, which we'll just say is the 50,000. So it'll be 50,000 squared plus the 37,500 squared. And what we should find and what we should get here is that c, or our hypotenuse, should be equal to 62,500 kilograms by meters per second at some angle. We'll find theta here in a second. So this right here, I mean, we've got half the answer already. We just have to find theta. This is what we should expect. This should be or I shouldn't say this is our final answer because we still have to do this. Sorry. So we've got the final momentum. Let's see what the final velocity should be. So we'll divide that by 4,000, okay, because that is our final mass here. It's the combined mass. And what we should see here is that we should have 15.6 meters per second for our final velocity. Okay. Let's find theta. Theta will use again, we can't use these guys here as great as it would be. We still have to account for the masses of each of them because they're different and they're moving at different rates. So we've got to use the units and the measurements that take into account both velocity and mass, which is momentum. So we'll say, and we only have this, we'll say that we didn't find this. We only have these two. So we'll say tangent of theta is equal to the opposite over adjacent. Okay. Use inverse tangent. And then we'll put opposite over adjacent. So opposite, meaning 50,000 over 37,500. And we'll get theta equaling 53.1 degrees, which is what we should have expected. Real quick, just to think about that. The truck has a higher momentum. It has a higher momentum of equaling 50,000 over the 37,500 from the car. So we should expect that when they combine into one mass, we should expect them to move together closer to the direction that the truck was moving in due to its higher momentum. Okay, that just makes sense. If it was below 45, something went wrong. Okay, if it was below 45, then maybe we got these mixed up here. Okay, because that's not what we should expect. We should expect that the object with the higher momentum to kind of carry both objects in, relatively speaking, the direction closer to its original direction it was in motion in. Okay, so 53 should make sense. That is what we should have expected to some degree. Okay, so now we got theta, and then we would have pretty much our final answer. We would then say that its final velocity of both objects here would be 15.6 meters per second, 53.1 degrees north of east. Okay, and we would have our final answer. Now, that's all good and dandy. We can do that. That's simple trigonometry, really geometry. It's almost a crime to say trig, even though it is a right triangle, but we can do that easy peasy using that. Now, Another way we can do this is using the conservation of moment, or the law of conservation momentum equations formula. So remember, that's going to be, m1 times the velocity of our first object plus the mass, mass of our second object is going to be equal to, and this is, since it's a completely inelastic, it will be we'll see the mf, which is going to be the combined 1 plus 2, times the final here, which is going to be the velocity of both objects. Okay, we would use this, right? So, so we can say that, okay. But we can also say, and this is broken down, but since we are now we're not moving in the same line here, there is somewhat of a difference. So we can start off with using this, but we've got to make a change here, okay? And technically speaking, we really should put this into x and y's. So let's split this up in x and y. Let's do the x here. We're going to do the x direction. So it'll be like m1 v1 plus m2 v2. Okay, or this will be the car, this will be the truck. So we'll say actually mc vc mt vt is equal to mf vf. Okay, well, there's some we got tech on here too. Just hold on a second. But before I do that, just recognize the truck isn't moving anywhere in the x direction here. So we can just get rid of it. Okay, so then what we're left with is the mass of the car times the velocity of the car should be equal to the final mass, which will be the combined mass, times the final velocity. Bummer though, we don't have the final velocity, but we do have a way in which we can find the final velocity, which is going to be the mass of both objects times the velocity of both objects times, if we're looking at the initial momentum of our car, this will be the final velocity of both objects times the cosine of theta, okay, which makes sense because what we're doing here is that we're pretty much trying to find whatever the final momentum is here, more or less, of our car in the horizontal. That's what we're doing here, more or less. Okay. And what we can do here is then we can solve for this guy because we don't know what that guy is. We've got this, we've got this, we've got these over here. Okay, so let's just solve for VF. So easy peasy, all we got to do is move these two over. So it'll be the final velocity is equal to the initial velocity of our car divided by the final mass times the cosine of theta. And if we plug that in, okay, so that'll be the 37,500 times the combined mass times the cosine of theta, which, and I'm assuming that we've already found theta, and we did find theta on the other side. This is, 53.1 degrees. And what we would find out here is that when we pop this in, we would get 15.6 meters per second, which is exactly right. And then we would put in our theta as well, 53.1 north of east. And then we would have our answer. And then if you're skeptical of that answer, and if you want to double check, literally do the same thing you did here, only instead use this. We would do this. We would say final velocity, and instead of using the car's initial momentum and the cosine of theta, rather we'll use the truck's, okay? And in this case, because the truck is moving north, we'll use sine. So what that'll translate into is 50,000 over 4,000 times the sine of 53.1. which you will get 15.6, okay, which is awesome. So that would find our final velocity for both of these objects here. We double checked here with they both have the same velocity. They're at the same, they're traveling together as a combined mass at the same angle. And then you can do this. You can then double check to make sure that you have, the correct momentum. So we found previously, using Pythagorean's theorem, we found out that the final momentum is 62,500 kilograms by meters per second. Okay, that was the momentum of our hypotenuse here. Well, let's just double check. It's 15.6 times 4,000. What do we get? 62,400. So using our momentum, conservation of momentum equation here, okay, we can find pretty much the same thing as we can with Pythagorean's theorem using momentum, okay? And we can then double check our answer by finding, or after using the conservation of momentum, we can then double check that by using against Pythagorean's theorem by multiplying 15.6 times 4,000, which gives us 62,400 kilograms by meters per second. Okay, which is awesome because that's pretty much what we found on the same side or on the other piece of paper, which tells us that we have a conservation of momentum. We have the same velocity for both objects as they've combined into one mass, which means that we should be pretty close to the true answer. Okay, and that is check your understanding number 1. So I'll have check your understanding number 2 and number 3 on 2 separate videos. So if you have any questions, make sure you get a hold of me.